Hello. In this video, we will try to see how we can calculate the center of mass for a solid object with non-uniform density. We will be able to identify these kind of problems in the AP if a linear density function is given and we need to find the center of mass. Now, before we go to see how we can do that, let's try to remember a few things. First thing we need to see is the center of mass for a solid object of uniform density. In this case, it makes sense that the center of mass will be at the geometrical center of the object. Sometimes it's easy to locate the geometrical center. Sometimes maybe we'll need to find the diagonal of the object, and from the coordinates of the diagonal, we can find the center of mass position, the x of the center of mass. Sometimes maybe we'll have a collection of particles, and in this case we need to identify what is the location of the center of mass of the first object, the center of mass of the second object, the third center of mass, the fourth center of mass, and the fifth center of mass. And if we know the mass of each single particle or of each single object that forms the system, we can find the location of the x-coordinate of the center of mass by applying the rule x1 times mass 1 plus x2 times mass 2 plus x3 times mass 3, and we keep repeating this addition for as many particles as we have. In this case, we have four particles divided by the total mass. In this case, it is m1 plus m2 plus m3, m4, and m5. So from this law, we can find either the x-coordinate of the center of mass, or we can repeat the calculations for the y-coordinate of the center of mass. However, sometimes maybe we'll have something a little bit more complicated, like we will need to find the the center of mass for a solid object with a non-uniform density. Now, what this practically means, if sometimes we have a complicated system, for example, the wing of a plane that is thick on one side and thin on the other side, it means that its mass density is not uniform. There is a large density value close to the fuselage of the airplane and almost zero or very, very close to zero density value for the part that it is near the wingtip. So it makes sense that the center of mass will not be exactly at the geometrical center of the wingtip, but it will be located closer to the side that it is near the fuselage. In this case, there will be a linear density function that needs to be identified. Or we might have a material that can be dense on one side and less dense on each other side. Now, this can happen in case we have an object that, for example, glass, that gathers mass downwards under the influence of the force of gravity. So it makes sense that there is more mass density on the bottom side of the object compared to the top of the object. Or if you have a fluid, and again, there is a linear mass density that it is not uniform. It changes with the position x. So we will have probably a linear mass density that will be, for example, a times x, and this means that if my origin is on the left side, as the value of the x, as the value of the position x increases, the density increases. Now, in order to find the center of mass, in this case, we are using a similar law to the one that we just said before, which was that the center of mass position, it is summation of xi multiplied by mi divided by the total mass, which is summation of mi. Now, in order to find the center of mass in this case, we consider that each segment of my object is made out of small, infinitely small mass, that it is dm, and it has a length that it is dx. So there is a linear mass density that it is mass over length, or in this case it is dm over dx. And the position of the center of mass, it is, instead of summation, we are saying that it is integral of x times dm divided by summation of its dm. Now, how can we apply this? In case we have an object that has a linear mass density, that it is given as a function of position, it is 2x, what we need to do is sooner or later apply the law that the x of the center of mass is integral of x times dm divided by integral of dm. And in these cases, most likely what will be given to us is the length of this object. In this case, the length, it is 2 meters. Now, the problem with this integration is that it is an integration for dm, but what we know is a length. So somehow we need to change the differential dm to something that contains length or position x. In order to do that, we take the linear density lambda, which means dm over dx, and we solve for dm. Now this lambda is 2x, so we have 2x is equal to dm over dx, and the dm is equal to 2x times dx. Now, what this means is that we can remove the dm from the two integrals and replace it with something that has position x. So we say that it is integration of x multiplied, instead of dm, we say 2x times dx, and then again integration of, instead of dm, we can say 2x times dx. So we get an integral for position x, but the position x changes from the position 0 to the position that it is the final length of the object. In this case, the length is 2 meters. So our integration happens to be from 0 to 2 and 0 to 2 for both integrals. So we have the integral from 0 to 2. We have 2x and then again multiplied by x, so 2x squared multiplied by dx divided by integral of 0 to 2, 2x dx. Now, either we can calculate these two integrals manually, or if we go to the calculator for each single one of them, at the end, I believe that we will find that the value of the position x of the center of mass is approximately 1.33, in this case meters, which makes sense because since the density of the object increases as we move to the right, and we saw a representation of this somewhere here, if the density was uniform, then the center of mass would be exactly in the middle. It would be at position 1 meter, 1 out of 2 meters. But because the density of the mass increases with the position x, it makes sense that more mass is found on the right side of the object. So the final center of mass is not exactly at 1 meter, it is at 1.33 meters. Thank you for watching. Feel free to comment if you have any questions.